This is just a basic tutorial on how to carve surface mount device footprints with a Dremel, or in this case a zoomed out too far, a Ryobi branded equivalent tool to a Dremel, but it's effectively the same thing, just by a different manufacturer. And focus. Focus. Thank you. This is just a way of doing device footprints and eval boards for these kinds of integrated circuits without having to use any kind of a photographic or chemical process like toner transfer or typical photographic PCB manufacturing techniques, which are fairly common but fairly complicated and generally not worth the effort if you're only just cranking out a simple eval board. Now the first step is with a very fine pitch pencil. Preferably one with a nice sharp point so you can do really nice fine lines. Is just mark out cut lines in between each pin of the integrated circuit, like so. Now this particular IC that I'm using is an LM2936 HVMA 5-volt potential regulator, so I'm not going to be carving out all of these cuts because pin 2, pin 3, pin 6, and pin 7 are all electrically connected. Those are all the ground pins on the IC, all connected to a common lead frame inside the device, and pins 4 and pin 5 are not used at all. Those are just non-connected. But in some versions of this IC, pin 5 is a remote shutdown control pin. Just so that for power management, the IC and whatever it's running can be just shut off. After making your marks on one side, you'll just want to check to make sure that the alignment is good. And then repeat on the other side of the IC. Ordinarily I just use my finger, but so that the process can be seen, I'm just using this pencil. Another thing, make sure that the IC doesn't move around a lot, because again, being surface mount, extremely fiddly. And this is comparatively easy to solder and manipulate by surface mount standards, so be careful. Here, once you have the device aligned on one side, repeat your marks on the other. And check to make sure that everything is in alignment. It looks pretty okay so far, although... Oh, got it. Alright. In this case, a bit far apart, so just need to reconfirm alignment on my one side. Just repeat the marking process. And next step is just look at the board from an angle, make sure that the lines are actually match up, which is important because otherwise you'll screw up your cut. Yeah. I'm filming this with a remote monitor, so it's kind of tricky to get the thing in the shot. There we go. Now your next step is to carry each line through across the IC. Now again, I'm only doing this for some of these because again this IC only needs a couple of these to be separated, but ordinarily what you would do is this line would be carried through all the way across the IC, and each of these would be brought out to a separate pad. Like for example this one, which would be pin 8, this, you'd separate this out, make it its own pad, and then what you do is you cut, or you do another line like this, separating those out into their own pad, and another line separating that onto its own pad, etc. Like for example, there. Like for example, what I did on this ACS 713 Hall effect current sensor eval board, if I can get it in this shot properly, and now this one also has some pins on the IC tied together because pin 1 and 2 and pin 3 and 4 are the measured current pins. But if I can bend that cap out of the way, you can see how I just brought that, or each of these pins is brought out to its own separate pad to make us soldering on connection wires easier. But anyways, now once you have just a lot of confusion, I'm going to erase a lot of those unnecessary lines. Now what you do is with a very, 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 very fine pitch, or very, very thin cutting wheel. You want it to be very thin because the grinding wheel can be no wider than the pin spacing in your IC. You're going to want a very, very thin one. And just as a word of warning, this technique will only really work as far as 50 mil pin spacing ICs, like for example SO-8 devices or SO devices. Although when you get probably above 14 pins, it's going to be tricky doing all just the breakout thing, because you need to cut a number of very fine parallel traces, and that's going to require mad skills in the steady hands department. But anyways, now once you, and also a safety tip, stay out of the plane of rotation of the cutter, because if these let go, otherwise having bits of cutting wheel embedded in various bits of your anatomy, which would be somewhat injurious to the health. So again, something to avoid. Now, this is probably something that should be done with the tool off first. Line the cutter up with one of the lines that you're going to be cutting. Then turn it on and start. Now another really useful trick is that keep the bit that you're cutting attached to the whole bit of PCB, as it makes handling the printed circuit board substantially easier, as you can see I'm doing right here. And also clean off the cutting swarf at regular intervals, just so you can more easily see what you're doing. Now once you've done that, make your second cut. And that's all the cutting finished so far. Now, visually inspect the board. One good technique is to shine a light through from the other side of the PCB, and just make sure that there aren't any dark spots in each line. Another option, once this thing has been cut free of the main bit of PCB you're carving it out of, is just a resistance check. Go through every single pad, check and compare that to every single adjacent pad, and just make sure that there's no continuity between anything. Now, once you finish your carving on all the traces, now it's time to cut the board loose from the end of the PCB. Also be careful not to breathe in the dust. Because again, not the best stuff to be breathing in. And especially not if you're doing FR4 or fiberglass boards. Snap loose. And just for partly cosmetic reasons, partly for safety reasons, just want to sand that down once you're done cutting it up. Now, once you have your PCB carved, next step is to solder on the integrated circuit as well as any additional components. In this case, I'm going to need an electrolytic capacitor for the output, and because I have a very minimal stock of surface mount components, and as a consequence, I'm using a dead-bugged through-hole component, a input capacitor for the input of the regulator for stability purposes. In this case, this is a Corning Glassworks glass dielectric 100 nanofarad cap, because again, is what I had, because I've got a lot of them, and a 330 microfarad 6.3 volt electrolytic for the output. Again, what I had. Yes, it's way overkill for the application, but again, minimal stock of surface mount components because almost all the stuff I do is through hole. Now, one thing that comes in, or a couple of things that come in very handy soldering very fine pitch stuff like this. Very small tip on your iron. This is a 31 mil, I think, tip on a Weller SPG 40. It's my everyday soldering iron. We get, again, very high quality stuff, which helps because the replacement tips for these are about the same price as your typical crappy, cheapy Harbor Freight soldering iron. But again, they're much better irons. This whole soldering station is part of a there's a WL100 or WLC100 soldering station. Retails new for about 50 bucks. So another thing that comes in really handy, flux. And it really helps as far as just soldering and surface mount devices, and it's somewhat sticky when the solvent evaporates, but that of course means it's very hard. It's nightmare to clean up, so again, be careful about not spilling it. And very fine pitch solder. This is multi-core 15 mil 6040 lead tin solder, or 60% tin, 40% lead, you know, proper stuff, none of this rose nonsense. Again, first step is again, apply a little bit of flux to all the joints you're going to be soldering. Zoom in a bit. Then, after making sure that the device is aligned, tack one pin and being careful not to overheat the device again. Short dwell times are very important. And this is going to involve bridging at these pins, but they're designed to be, so that's not a problem. Just don't do it if you're doing other ICs that can't handle that. Solder. I'm going to just blow on it a bit just to cool it down. And again, a lot of this is just short dwell time, which is of course pretty much any kind of soldering any thermally sensitive stuff. And doing it right the first time. I just need to go back and do a couple of dents on this side of the board. There you go. Now just want it to cool it off and just visually inspect to make sure it's all nice and happy and everything looks good. So now for the extraneous components, the additional ones. That's the electrolytic. Again, same procedure. And also for devices like, or for cases like this, you want ones that have pins that ride up on the side of the integrated, or on the side of the device, because then it makes soldering them in this manner much easier. For ones where the pins are hidden, or the contacts are just on the bottom of the IC, this is very hard, and then probably going to have to dead bug it with wires onto a board. You can just put solder on your flux on each end. Now, because this is a field, you're going to just turn the iron up a bit. Again, just apply your solder. Yep. That's the first one. And the second one. Reheat that turn a bit. There we go. And now, last but not least, the capacitor, or the input capacitor. Now for these, just bend the leads so that they're heading out at right angles to the main component, like so, and then do some 90-degree bends so that the leads are about flush with the base, with one side of the components that are roughly flat on the board, like so. Now set the component down, adjust the leads to make sure that they're flat on the PCB, and solder, or bit of flux, and solder, just to make it that much easier. Come on. There you go. Stay there. There's one problem with surface mount. There's nothing to really hold the pins down, but you can manage. Now, let's solder like so, and then this one, because it's hokey looking, just a bit of extra solder, and boom, done. Now, with your side cutters. Again, this is another thing you want. Good side cutters. These are some American-made Crescent ones. About 14 bucks at Home Cheapo for a set of a pair of these and a pair of pliers. But they're substantially better than just about every set of cheapy, crappy Chinese ones that I've seen. Those are generally absolutely horrible. Now, last step, wires. Grab them. Come on, go. And your wires, and these ones I've already pre-stripped. But for the side that's going to mount on the PCB, you're going to want about roughly a 1/4 inch of stripped wire. And where it's going to be connecting on the board. For the other end, you strip them however long you need to make your connections to your other wires, but generally about 1/2 inch is fairly okay. These ones, of course, you can strip them longer if you need to, once they've been mounted. so transparently. Now, once you've got your wires on your pads, solder. So flux first, then solder. So dab. Blink. Blink. And blink. Come on. And it also helps with some of these, if you hold the wire down with something like a weight or something. I'm just using my side cutters. And just solder. Now for some of these bigger joints, or for ones that are going to require more solder, you generally want to use thicker stuff because precision isn't anywhere near as critical. That's for this I've got 32 mil solder. This is Kester. Again, 60% tin, 40% lead. None of this rose crap because lead-free solders generally require much higher temperatures, so much more likely to fry devices on your board. They also can develop fairly nasty metallurgical failures. Come on. Like tin whiskering, another miscellaneous not good. And also because there are a number of different alloys, many of which are incompatible with each other, and reworking with an incompatible alloy from what the board was originally made with can lead to fairly nasty failures of the equipment, which is why lots of critical communications infrastructure, I think some medical stuff, pretty much anything where if the device fails, all kinds of horrible, nasty, not good is going to happen. They're specifically exempt. Like, I think also avionics, a lot of that's exempt. Just because it's a piece of crap. Now, of course, consumer stuff, they generally don't care because the stuff's only designed to last for about 2 months. But, anyways, it's just very stupid. I know one of the many reasons why I don't like the Enviro Eats, but there you go. Finished board. And in this case I used, also just for ease of marking, just use a yellow, which is a fairly standard hot color in computers for 12 volt stuff, or positive 12 volts, and red for the 5 volt output, and white for the ground, which is my own standard color because it's the standard neutral color here. But yeah, just as long as your wiring plan makes sense, like no blue neutrals. And that is the finished board. And fairly fast way of making boards once you're used to it. And just to show that the finished board is in fact working, this is it running a 5 volt LED indicator lamp cartridge. Mounted in this little Dialco panel mount light. It's a little pin-based cartridge because lots of equipment used to have these where they had either incandescent gray and wheat lamps or neon lamps mounted in cartridges like this, and when LED lamps started becoming common, you could get LED replacement cartridges for these to replace the incandescent lamps, which was something that was a bit more reliable, lasted a very long time, although the incandescent lamps frequently lasted many thousands of hours. But anyways, it works, because this is designed for 5 volts, and it's a 5 volt regulator, so actually, and it's running on a 12 volt battery. Although this particular regulator will work up to 60 volts input, which is one of the reasons why I got them. But anyways, it works. Yay.